Okay, so let's continue with our lecture. The last time we finished our section on quantum operations, and then we started with the new section, distance measures. And our motivation was that we want to find out, or we want to quantify how different two quantum states are. Okay, so as an example, we said, suppose that Alice sends a message to Bob through a noisy quantum channel, and he receives rho prime instead of rho because there's some noise. And then we ask, how can we quantify how close rho prime is to our initial state rho? Right. So this was one motivation, and in particular, those comparison of different quantum states you will encounter everywhere in quantum mechanics. Okay? Because at some point you always want to see how close is the state to some other state. And we then also started a little bit with discussing classical distance measures in the sense that we started motivating this. Okay? And the reason is that a quantum state, or a density operator, is a generalization of a classical state. And as a classical state, I mean a probability distribution. And last time we've also seen kind of that classical information can be modeled by a random variable, okay, usually called x, which has some outcomes, say a1 to an, which appear with some probabilities p1 to pn. Okay, and then as the classical state, we can associate this probability distribution. Okay, this is what we can see as the classical state. And how we motivated this, that we can model classical information via such a random variable, is we again suppose that Alice is communicating with Bob, and they share a so-called alphabet, which are these A1 to AN. So these are the letters in this alphabet. And we assume that these letters appear statistically independent with these probabilities P1 to Pn. Okay? And then depending, and both the alphabet and the probabilities are known to Alice and Bob, right? And now Alice can prepare a message which she can send to Bob. And we've seen that in the extreme cases, for example, if we have, so we consider two extreme cases. One case was that P3 was, the probability of P3 was 1, and Pj was 0 for j unequals 3, right? And then the message of Alice must be A3, 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 and so on. Okay? And we always consider the limit of infinitely long messages. And in this case, there is no information in this message, because Bob already knows what this message is going to be, because he knows this probability distribution, right? So he can be certain about what the message will be. So there's no information content in this message. And then as a second extreme case, the other extreme case, we consider that all probabilities are equal, so it's 1 over n. And then, so for all j, and then the message is going to be some message, say A3, A9, A4, and so on, right? And now Bob is maximally uncertain about what the message will be, right? Because he knows these probabilities, and if they are all equal, then he's maximally uncertain, and then this message has maximal information content. Okay? But our motivation was that we can now quantify information by considering this probability distribution. And if you want to compare now two different classical states, so different classical information, we have to compare probability distributions. Right? And this I think so far became so far last time, and now the task is to compare two different probability distributions, right? So this is what we're going to do next. And we do this now via, so the first measure that I introduced with which we can compare probability distributions is the so-called trace distance. So this is now definition 3.2. So the trace distance sometimes also called L1 distance or Kolmogorov distance. between two probability distributions let's call them capital P being the probability distribution Pj, and say capital Q is the probability distribution with probabilities Qj. And these probability distributions, they run over the same index set. So over the same index set. And we define now this trace distance, which we denote by capital D. So it's now D of the P and Q, which we also write as D of Pj Qj. And this is 1/2 times the sum over all j, and then we sum over the modulus of the differences of these probabilities. Okay, so that's how it's defined. We take always the modulus of the differences and then sum over it, right? And then we have a factor of 1/2 for normalization. Now let me state some remarks. So in particular, one remark, namely the trace distance is a so-called metric on the space of probability distributions. Okay, and this goes with some properties that the metric satisfies. So let's write this down. So the trace distance is a metric on the space of probability distributions since it satisfies the properties of being a metric. Okay, and the properties are as follows. So first, it's non-negative. Meaning that the trace distance d of P and Q is greater or equal to 0. Then the second property is that the so-called identity, namely that the trace distance of P and Q is equal to 0 if and only if P is equal to Q. Okay? Meaning that the distance is 0 if and only if we have the same probability distributions. Identity. And the third is the symmetry, which says that the distance between P and Q is the distance between Q and P for all probability distributions Q and P. And then the fourth property for being a metric is the so-called triangular inequality. Meaning that the distance between P and, say, R is smaller or equal to the distance between P and Q plus the distance between Q and P. Okay, so being a metric means that you can indeed use this in this space of probability distributions as a distance measure, right? So imagine, for example, you have here the space of all probability distributions, and here you have some the probability distribution P. Here you have R, and here Q. right? And then it says that those P and Q are equivalent if and only if the distance is 0, so if and only if I'm here at the very same point in the space, and so on. So, and for example, the triangular inequality, you see that this distance PR is smaller or equal this distance plus this distance, right? And this is what, if a measure satisfies these 4 properties, then we call this a metric, right? So this is now the first measure between classical probability distributions that I wanted to introduce. And I also would like to introduce a second one, which is the so-called fidelity. And as you will see in a second, the fidelity is actually not a distance measure, but instead it is a similarity measure, right? So the distance measure is 0 if and only if they're equal, and if it's maximal if they're as far apart as possible. Now the fidelity which I introduced is a similarity measure, which has kind of inverse properties in the sense that is 0 if they are maximally different, and if it's 1 if they're maximally similar, so if they're equal. So this is our definition 3.3. The fidelity between 2 probability distributions call it again P and Q on the same index set. Is defined as follows. So we call this F of PQ. Okay. Sometimes write this as F of PJ QJ, which is the sum over the square root of Pj times Qj. So you now see that this kind of reminds us already on the inner product between 2 vectors with elements square root of Pj and elements square root of Qj, right? So indeed you can see this as being an inner product, and as we will see today and possibly also next time, that this is going to be a kind of a good picture, which also then translates to the quantum counterpart of the fidelity. So let me give some remarks. The first thing is that the fidelity is the inner product between 2 vectors. Let's call them the vector P, which is square root of P1, square root of P2, and so on. And the vector Q, which is square root of Q1, square root of Q2, and so on. And they lie on the surface of the unit sphere, right? And this is since, if we take the modulus of these vectors, then we simply sum over all probabilities, and this gives us 1 because we're dealing with the probability distribution. So you can think of Q, the vectors Q and P living in a high-dimensional space, right? And these elements correspond to the square roots of the probabilities, and the fidelity is then the inner product of these, right? And in this picture, we already see that the fidelity gets 1 if and only if I have the if and only if P is equal to Q, right? Because then we're fully overlapping. So, and this is actually my second remark. Also, what I said before, that the fidelity is not a metric. Okay. So it can be seen as a similarity measure. And it satisfies 0 small equal to the fidelity P and Q small equal 1 with, as I just said, f of P Q equals 1 if and only if f is equal to Q. So here I'd like you to keep in mind this picture of this the fidelity being an inner product between two vectors, right? Because we're going to encounter such a picture also in the quantum case. But before we go to the to the fidelity in the quantum case, I'd now like to first I'd like to discuss the trace distance. So with this, I'm kind of finished now with the properties of these two measures between classical probability distributions. And what we're going to do next is now we're going to define some generalizations thereof, which measure differences between density operators, right? So in the first measure that I define is the quantum counterpart of the trace distance, right? And then we're going to prove some important properties of this quantum trace distance, and then we're going to continue with the fidelity. Okay, so our next section, subsection 3.3.2, which is the trace distance. And let me stress that if we say trace distance, it's not specified whether we mean now the classical or the quantum one, right? But in the context, it's usually clear whether the classical trace distance or the quantum trace distance is meant. So we now generalize the trace distance. It's here 3.69 to the trace distance between two quantum states. So in a second, when we define the quantum trace distance, you will see why it is called trace distance, because it involves the trace of a distance, or better, the trace of a difference, actually. So this is definition 3.4. The trace distance between two quantum states rho and sigma is defined as d of rho sigma equal to 1/2 the trace and then of the modulus of rho minus sigma. So where the modulus of an operator A is the square root of A dagger A, with the square root being the positive square root of a positive semi-definite operator. Or semi-definite matrix. Okay, so this is now the way how we define it. And I hope you're comfortable with this, because we already encountered several times the modulus of some operators, right? And I just wrote it down. The modulus is the square root of A dagger A, with the square root being the positive square root of a positive semi-definite matrix. And most of the times it's A. So in this way we can find a spectral decomposition of A, and then it simply write down A in the spectral decomposition and take the modulus of all its eigenvalues. That's how you usually calculate this thing. So don't be afraid of these expressions. They're not hard to calculate. Simply always think of it's easy to think of the spectral decomposition and then taking the modulus of all eigenvalues. Right? And then, so we are calculating the difference here, and then the modulus of this operator, and then we're taking the trace. Right, now the first question is now this trace distance on the level of quantum states also a metric? Now, we ask, is this a metric on the state space of quantum states or of density operators? And the answer is yes. So the trace distance is a metric on the state space, or on the space of density operators since it satisfies I, again, we have non-negativity, meaning that d of rho sigma is greater or equals 0. Then the second property was the identity, namely that d of rho and sigma is equal to 0 if and only if rho is equal to sigma. And the third one is the symmetry, namely that d of rho sigma is equal to d of sigma rho, and the fourth property is the triangular inequality. That d of rho, say kappa, is smaller or equal to d of rho sigma plus d of, sorry, I said it wrong. Here we have sigma kappa and then sigma rho kappa. Okay, so those properties are actually, most of them are easy to see. So the first three properties we actually see immediately. So non-negativity is clear, identity is also clear, then symmetry is also clear from the definition. The only thing which is not that trivial is the triangular inequality, right? If you want to prove this, I'm not showing the proof now, but I think you can just do the proof by your own. Actually, you possibly proved this in the exercises. So now let's continue with the second remark, and this is an interesting remark, namely that the trace distance is invariant under unitary transformations. So, meaning that if I transform rho and sigma via a unitary transformation, then the trace distance between those states, it's intuitive that this happens, because what we do with the unitary transformation is we simply change the basis, right? And a basis change should not change the distance between two quantum states in the state space. So let's write this down. The trace distance is invariant under unitary transformations. So we have d of u rho u dagger u sigma u dagger is equal to d of rho sigma. The next remark that I'm going to state is quite interesting, because it already gives the first connection of the quantum trace distance and the classical trace distance. So think about what happens if rho and sigma commute, right? If rho and sigma commute, they have a common set of eigenfunctions. And in this case, we can transform via unitary transformations, which do not change the trace distance, into this eigenstate, right? And what we end up with is then the classical trace distance of their corresponding eigenvalues. So this is our remark 3. If rho and sigma commute, then their trace distance is equal to the classical trace distance. D of Rs between their eigenvalues so R equal to Rj, so which are the eigenvalues of rho, and call this capital S Sj of sigma. Okay, so I think also you're gonna do the formal proof of the statement in the exercises, but it's very easy to see if you transform into, if you go with the unitary transformation into the spaces of rho and sigma where they have the same set of eigenvalues, of eigenvectors. Right. Then it's very easy to see this. Then the last remark is what happens if we have qubits. So if rho is equal to 1/2 identity plus, let's call this R times sigma. So this was the way how we write down density operator of qubits in terms of this Bloch vector R, right? So let's express rho in this way and also sigma. And sigma is equal to 1/2 1 plus S times vector sigma. So don't mix it up with the Pauli operators, right? So this is a density operator and these are the Pauli operators. If rho and sigma describes a qubit on the Bloch Bloch vectors R and S respectively. Then the trace distance of rho and sigma is the modulus of R minus S divided by 2. So, and as I said, the proof of 1 to 4 is possibly going to be an exercise. Okay, so yet what we've seen is that there is a relation between classical and quantum trace distance, right? We've seen a relation if rho and sigma commute, but in general they do not commute, right? However, there is a very important relation that they do have, which I'm now going to state in terms of a theorem. And this theorem is related to a measurement that we perform. Right? So it says, suppose we have two states, rho and sigma, and we perform any measurement described by any POVM. And what we get out from these measurements are probability distributions. Right? And with these probability distributions, which are the outcomes of the measurement, those we then can compare by this classical trace distance. And what this following theorem tells us that the classical trace distance that we can calculate from these outcomes of any measurement is bounded from above by this quantum trace distance. Okay, so let me write this down. It's theorem 3.4. So let the set EM be a POVM. And let PM equal to trace EM rho and Qm equal to trace Em sigma be the corresponding output probabilities. By measuring rho and sigma, then the trace distance between rho and sigma is given by a maximization over all POVMs of this classical trace distances, Pm, Qm. There, the maximization is running over all POVMs. Okay, so this is a very important statement that now connects the classical and the quantum trace distance. So we see that the quantum trace distance is given by a maximization over all POVMs of this classical trace distance, meaning that it is an upper bound of the classical trace distances. So as a picture, really have in mind that we have two states, rho and sigma, and we now try to figure out how different they are, right? And what we do is we perform a measurement on this state, right? And we perform it for rho and we perform it for sigma. And from this measurement result, we then calculate the classical trace distance. And this classical trace distance is now bounded from above by the quantum trace distance, right? Because we can never get a higher classical trace distance than the quantum trace distance. And in the following, we're going to prove this theorem. So let me start with the proof. Well, the reason why it is so important is that if you're dealing with quantum states and with, say, a communication protocol or so whatsoever, or you are in the lab and you have two quantum states and you ask, are they different or not, right? The only thing that you can do is you can do measurements, right? Because you have to do measurements in the end in order to get some information about the state, right? And what you get out of the measurements are then probability distributions. And this theorem states states a property of the outcome of these measurements. And we're saying that the difference of this probability distribution is bounded by this trace distance. So it's a statement of what can you actually measure. So how is your measurement outcome bounded? And it's actually also an interesting result if you think about this this communication protocol between Alice and Bob, where Alice sends Bob a message through a noisy quantum channel, and we get, instead of rho, Bob gets rho prime, right? And we can suppose now that this quantum channel, that this noise is only very, very small. There's only very little noise in this channel, meaning that rho and rho prime are very close together, right? Meaning that this distance is very small. And then what this tells us is that no matter which measurement we do, so any measurement will lead to probability distributions which are also very similar. Okay? So if the left-hand side is small, then the right-hand side must also be small. Okay. So possibly one way of writing this down, so before I start the proof, one way of writing the statement 3.74 down is also that you say that the trace distance between the classical trace distance, if I perform any measurement on rho and sigma, is bounded from above by the quantum trace distance. Okay, this is what it tells me because I have the maximization, right? With equality in the case of my maximum. Right? But if I do any measurement, then this will be bounded from above by the quantum trace distance. And now let me restate what I just said is if this channel through which we do our communication between Alice and Bob, if the noise is only very little, meaning that the distance between rho and sigma is very small, then this means that no matter which measurement we do, we will always get probability distributions which are very similar. Okay. But on the other hand, if my noise is very big, so I have a lot of noise, and then this trace distance is possibly very, very large, and if I then perform measurements, then the difference of the measurement outcomes can be very large. It's not necessarily very large, but it can be. Right. Okay, so let's prove this statement now, or let's okay. I think we're going to prove it after the break. So let's do a break and prove it in 10 minutes. Okay, let's continue with our proof of the theorem which I just left on the blackboard. And we simply start with an expression for this classical trace distance that we've had before on the blackboard. So we have d of qm or pm qm equal to 1/2 then the trace of not the trace, the sum of OM, and then we have modulus of PM minus QM. Okay, now let's plug in the expression for the probabilities. So we have the trace of EM times rho minus sigma. This is how we calculate the probabilities. And as a next step, so this is 375. So next step is we use that rho minus sigma is Hermitian. This means that rho minus sigma dagger is equal to rho dagger minus sigma dagger is equal to rho minus sigma, because rho and sigma are Hermitian. Since this is Hermitian, we can find a spectral decomposition with real eigenvalues. So not necessarily positive, but real. So we can write rho minus sigma as the sum over some real eigenvalues lambda, with real eigenvalues lambda j, and then the corresponding eigenvectors. And now let me put this into two parts, namely those eigenvalues which are greater than 0, and the part with the eigenvalues which are smaller or equal to 0. And then we have here lambda j And what we do is we define our operator. This one we define as Q. And this operator we define as minus S. Okay. And the reason is that now Q is a positive operator, right? Because it only has positive eigenvalues. And S is also a positive operator because those lambdas are all negative. However, we define this as minus S, right? Meaning that S is also a positive operator. And the next thing is that we recognize is that Q and S, they have orthogonal support. The reason is that those lambda j's build an ON basis, and they are also, meaning that they are orthogonal, right? And this means that Q and S have orthogonal support. So here we defined Q, or simply note that Q and S are positive operators. With orthogonal support. And accordingly, we have that the modulus of rho minus sigma is equal to the modulus of Q minus S. Okay, this is what's standing here. So we have rho minus sigma being Q minus S, right? And now since they have orthogonal support, we can write this as modulus of Q plus modulus of minus S. Okay, so because they have orthogonal support, we can split this. And the next thing is we use that Q and S are positive operators. So meaning that the modulus of Q is simply Q, and the modulus of minus S is simply S, okay, because these are positive operators. So we have this modulus of rho minus Q is Q plus S. And now let's calculate this expression here, this trace of what's standing here, so the trace of EM times rho minus sigma. The first thing that we use is we write this as capital Q minus capital S. So it's trace of EM times Q minus S. Okay. And now, a moment of thought, we see that this is smaller equal to the modulus of trace of EM and then with Q plus S. Okay. So we recall that Q and S are positive, and so EM is also positive, meaning we have here the modulus of two positive values, which lie between 0 and 1, so to say. And we can, so to say, instead of taking a minus, this must always be smaller equal to this expression with plus, right? And now we know that we only have positive values here, so this is equal to trace of EM times Q plus S. Okay, and then we can plug in what we have here, so Q plus S is equal to the modulus of rho minus sigma. So we have trace of EM and then the modulus of rho minus sigma. Now we can use this in here in this equation 375. So using this in equation 375 yields the following. So let's plug this in here. So we have d of qm or pmqm is equal to 1/2 sum over m. and then we use this here, so we have trace of EM and then the modulus of rho minus sigma. Now we use that the trace is linear, so we have 1/2 trace sum over m EM and then modulus of rho minus sigma. And this we know is the identity, which is the completeness relation of our measurement operators. So we get 1/2 trace of rho minus sigma, which is the quantum trace distance of rho and sigma. Well, this is almost what we want. Sorry, here must be a smaller or equal. Okay, because we have this inequality here in 377. So it's almost what we want. Let's go back to the statement that we want to prove. We almost proved this. The only thing that remains to be shown is that we can reach this equality. So we can find a PUVM such that there is an equality. Okay, this is our last step. And to see that the inequality, or that there is a PUVM for which the inequality saturates, choose a measurement with PUVMs or with PUVM elements EM projectors onto the subspaces or onto the support of Q and S. So if those measurement operators EM project on the support of Q and S, I write this down. So choose Q as equal being to the sum of sigma of all lambda j greater to 0, lambda j. So this one projects, sorry, let's call this PQ or E naught, okay, which is a projector onto the support of Q, and E1 the projector lambda j smaller equals 0 on the support of S. Right, if we choose this, then go here in this case, then we see that this inequality saturates, right? Because if E is a projector onto the support of either Q or S, only one of these two terms remain, because Q and S have orthogonal support, and then this is an equality. And this is the only inequality that we encountered in this proof, and this means that if you choose it like this, then this gets an equality. And with this, we finished the proof that the quantum trace distance is given by the maximization of these classical trace distances. So this finishes our proof. And the reason why I did this proof is because it has a very nice trick. Namely, you take an operator, which is Hermitian, and you split it into two parts, into the part with positive eigenvalues and the part with negative eigenvalues, such that you remain with two positive operators, right? And then you can use inequalities. And this is a very nice trick that is also also appears in other proofs. Right? And I actually wanted you to see this, that you can take these such differences of density operators and write it as in terms of two positive operators. So let's now come back to our question of how does a quantum operation, how does this affect now the trace distance, or how does it affect the states? Suppose now we have two states, rho and sigma, and okay, let's motivate this actually with an example. So let me state the following example. Suppose we have two states, rho and sigma, so there's Alice preparing the state rho or sigma, and say rho corresponds to a message that she wants to send to Bob, something like, okay, say yes, and sigma corresponds to no. Okay, so she prepares the state and sends it to Bob, and what Bob can do is he can do a measurement. Okay, so he can measure the state. However, this channel from Alice to Bob can be noisy, okay, and we describe it via a quantum operation. So what he gets is actually he gets either E of rho or he gets E of sigma. Okay, and given this state, he'd now like to find out whether he got yes or whether he got no, right? And if now, for example, Alice prepares rho and sigma such that they have orthogonal support, then it would be here at this point it's clear that if you measure it, you can distinguish with certainty whether you get yes or no. Okay? However, if you now go through the quantum channel to Bob, this quantum channel can be such that E of rho and E of sigma do not necessarily have orthogonal support anymore. Meaning, no matter which measurement Bob does, he might be uncertain whether he got a yes or no. Okay? And in the worst case, he has that E of rho is equal to E of sigma, and then he can say nothing about the message of Alice. Okay? And we now want to quantify, or we want to see, how does such a general quantum operation affect the trace distance. Okay? So, because if what I just said is that the trace distance is equal to 1 if they have orthogonal support, then you can discriminate them with certainty. However, d of E of rho and E of sigma can be smaller or equal to 1. Okay? And then if this is smaller one, then Bob cannot be certain whether he get a yes or no. And this we're gonna formulate now in terms of a theorem, which we call the trace-preserving quantum operations are contractive. So I can write it down here. So it's theorem 3.5, stating that trace-preserving quantum operations are contractive. So let rho and sigma be density operators. On the Hilbert space H, then if E is a trace-preserving quantum operation, then we have that the distance between E of rho and E of sigma smaller or equal to d of rho and sigma. So, and this tells us now that trace-preserving quantum operations can only lead to a loss of information. In a sense, if you consider the distance between rho and sigma as information, okay, simply think of this example here. The information would be yes or no to some answer, right? And under trace-preserving quantum operations, there can only be a loss of information given by this inequality that this trace must be smaller or equal to this one. Okay? And consider our example here. So in the case where this is smaller, Bob cannot be certain whether he gets yes or no. So there is some information lost due to this channel. And this is what this inequality tells us. So this tells us first, the proof is going to be an exercise, possibly. Proof exercise. And this tells us that trace-preserving quantum operations tells us that can only lead to a loss of information So finally, I'd like to state one more property of the trace distance, and then we come to the quantum counterpart of the classical fidelity. So there's one more property that is important for the trace distance, which is its convexity property. So I think for the remaining lecture I'm not sure, but possibly we are not going to use this property, but for completeness I'm stating it. Because I'm sure that once you work with the trace distance, you possibly come to a point where you would like to know this property. Right, so I myself used it quite often. But I'm not sure now whether we're going to use it at some point later on. But let me state the convexity property, and this is the theorem of the strong convexity of the trace distance. So it's theorem 3.6. So let Pj and Qj be probability distributions. And the set rho j and sigma j be density operators over the same index set then the trace distance of sum over j, pj rho j with sum over j q j sigma j is smaller or equal to the trace distance of pj and qj plus the, I think I wrote it like this, sum over j pj p of rho j and sigma j. Again, the proof, I'm not showing the proof. You can do it as an exercise. And now it simply tells us a property of how the trace distance behaves if I have such ensembles of states, right? So we have, as they said, Pj and Qj are now probability distributions. So I have a ensemble of some density operators here and here, and this tells us, okay, how does the trace distance behave if I have such an ensemble? And this is called now the strong convexity. And from the strong convexity, we get the usual convexity property. So namely, we find that the trace distance is convex in the first entry. I state this as a remark, okay, which directly follows now from strong convexity. So it's 1. We directly find that the trace distance is convex in its first entry. Namely that the trace distance of sum over j pj rho j with sigma is smaller or equal to sum over j pj, the trace distance of rho j and sigma. And okay, you might wonder why I specified it to the first entry. By symmetry, the trace distance is also convex in its second entry. Right? Is also convex in its second entry. Okay, so this is all I wanted to say about the trace distance so far. Now remember that how we came to the trace distance. So we started actually from a distance measure of classical probability distributions, and we then defined a quantum counterpart, which is a distance measure between density operators. So remember that the trace distance satisfies all properties for being a metric. So it is a metric in this space of density operators. And you should also remember its connection to the classical distance measures, meaning that the quantum trace distance is an upper bound of the classical trace distance, and that we can reach this bound for a specific POV M. Right, and now remember that for the distance of classical distributions, we also define the fidelity. And now what we're going to do is we define the classical the quantum counterpart of the fidelity. Okay. So this is now section 3.2.3. So the quantum fidelity is an important measure to compare two quantum states. And it generalizes, or it is a generalization of the classical fidelity. And we define the quantum fidelity as follows. This is definition 3.5. The fidelity between two quantum states is defined between two quantum states rho and sigma as f of rho sigma is equal to the trace of the square root of square root rho sigma square root rho. With the square root being the positive square root of a positive semi-definite matrix. Okay, so it has this very, let me say, very funny form with this double square root. So in the first moment, it's a little bit strange, right? And you might be a little bit afraid of this expression, but don't be afraid, okay? Because we know how to deal with square roots of operators. Again, think about the spectral decomposition. We do the spectral decomposition and simply take the square roots of the eigenvalues. So, meaning that you shouldn't be afraid of this expression. And the next thing is, even though this is kind of a nice expression, it's sometimes hard to tell some properties from this expression, right? Because for example, what's not definitely clear from this is whether the fidelity is symmetric. I mean, possibly you see it, that it is symmetric, but possibly you don't see it. Okay, so when I saw this expression the first time, it was a bit strange, and I didn't see many properties out of this expression. And that's why we can also rewrite this a little bit. But before we do so, let me state some remarks. So first, the fidelity can be interpreted now as a similarity measure, similar as the classical fidelity. Then it is symmetric meaning that f of rho sigma is equal to f of sigma rho. We will see this in a bit, and satisfies that 0 smaller equal to the fidelity of rho sigma smaller equal 1, with the lower bound being saturated if and only if rho and sigma have orthogonal support, and the upper bound being saturated if and only if rho is equal to sigma. Okay, we are going to see that all of these properties follow from a different expression of the fidelity. Okay, possibly we're going to state it today, otherwise the next time. So now, as a second remark, the fidelity is also invariant under unitary transformations. Okay, so if we simply do a basis transformation, then the fidelity does not change. And this is an important property for a measure with which we can compare states. Okay, so similar to the trace distance, the fidelity is invariant under unitary transformations. So we have f of u rho, u dagger, and u sigma. U dagger is equal to f of rho and sigma. And it also has some other properties which are similar to the trace distance. So remember how the trace distance behaves if rho and sigma commute. What we found there is that what we get out is the trace distance of and the corresponding eigenvalues of rho and sigma, as rho and sigma commute, right? And this very similar thing appears here, namely, if rho and sigma commute, then the fidelity is equal to the classical fidelity of the corresponding eigenvalues. So this is our remark number 3. If rho and sigma commute, then their fidelity f of rho and sigma is equal to the classical fidelity between their eigenvalues R and S. Okay, where these are the eigenvalues of rho and these the eigenvalues of sigma. And then, okay, let me now state what happens if one of these states is pure. Okay, so what you often have to do, for example, if you do an experiment, then you often have to compare a pure state with a mixed state. Okay, because what you get out from the experiment is usually a mixed state because there's some noise in the experiment, but possibly you ideally would like to have a pure state. So what you then often compare is pure and mixed state. Okay? if you compare a pure state and a mixed state, this expression takes a very simple form. So the fidelity between a pure state, let me call this psi, and a mixed state rho is as follows. Then we have f psi rho equal to the square root of psi rho psi. Okay, you see that this simplifies, and I think you're very comfortable with these expressions, right? And then the fifth remark is that what happens if we can compare two pure states, right? Then it gets even simpler. So for two pure states, psi and phi, and the fidelity is f of psi phi equal to the modulus of the overlap of psi and phi. And again, the proof of remark 2 to 5 is possibly going to be an exercise. Right, and the first remark we're going to see once we proved actually the Ullmann's theorem. And I'm going to state now Ullmann's theorem, and we possibly do some preparations for the proof then. So, okay, before we go on, let's now consider the state of pure states, okay? What we see is that it's the modulus of an inner product of those two states. And now remember what I told you when we discussed the classical fidelity. For the classical fidelity, we had the picture that we can interpret this as the inner product between two vectors which live on the unit sphere, right? These vectors were the square roots of all these probabilities. Right? And now there comes the connection that the classical fidelity can be interpreted as an inner product, and the quantum fidelity, at least for pure states, we see here that this can be seen as, it can be interpreted in terms of the inner product. Now, what Ullmann's theorem states, which is the theorem that I'm going to state now, it says that we can still interpret the fidelity in terms of an inner product, but if we have mixed state, then this is given by the maximization over all purifications. Okay, so it's theorem 3.7, which is called Ullmann's theorem. So let rho and sigma be states on the Hilbert space H. Then the fidelity of rho and sigma is equal to a maximization over purifications psi and phi, and we maximize the modulus of their inner product. Where the maximization is over all purifications psi, which lives in the Hilbert space H tend to H, and phi, which also lives in Hilbert space H tend to H. So this is psi of rho and phi of sigma. Okay, so Ullmann's theorem is a very important theorem for the fidelity, because we can immediately read off properties of the fidelity in this expression. Okay? Now remember our remark 1. Okay? In remark 1 we stated that the fidelity must be symmetric. Right? From this expression here, it's not intuitively clear whether it's symmetric or not. Well, possibly you see it, because it can be rewritten very nicely. But from this expression here, so from Ullmann's theorem, we directly see that the fidelity must be symmetric. We also see that the fidelity must be bounded from below by 0 and from above by 1, right? Because the overlap cannot, the modulus of the overlap cannot extend 1. And this kind of, from this we already see all of these properties that we stated in remark 1. We also see the property of remark 2, which says that it's invariant in unitary transformations. We'll do it here. The unitary transformation of psi and phi do not change this overlap. Okay, so we also see this property here. Let's see what else we have. Okay, this is possibly going to be complicated. Well, and the others are just special cases. So in the case of we see the almost all properties of the fidelity directly from this expression here. And the reason why it's also nice is this intuitive interpretation and this connection to the classical fidelity. That this can be seen as the inner product of the corresponding pure states. And here, if you're dealing with mixed states instead of pure states, then we have to consider the inner product of the purifications together with the maximization. So the proof of Ullmann's theorem is rather long. Okay, I think the proof of Ullmann's theorem is rather long, but we're going to do it. And we're going to do it next time. So it will take us some time. We will have to do some to prove some properties that we need. But I'd like to do the proof because it's an important statement. And the proof is not too hard, so we can do it in the lecture. And I'd suggest that we stop here for today, and next time we start with proving the theorem. See you next time.